Continuing now in chapter 22, looking at diseases that affect both the upper and lower respiratory tracts. So those affecting both the upper and lower include whooping cough, RSV, that respiratory syncytial virus, and the flu. Starting first with whooping cough, this is also known as pertussis, which is a type of cough. There are a couple different phases to these infections. So the catarrhal phase, this is the bacteria in the respiratory tract that actually causes cold-like symptoms. There's a paroxysmal phase. This is that uncontrolled coughing, which leads to that whooping sound, which is what it's named for. And this can actually cause the breaking of blood vessels in the eyes. It can even lead to vomiting and hemorrhaging if it's violent enough. And then we move into the convalescent stage, kind of the recovery, where the bacteria start to decrease. But what happens is those ciliated epithelia have been so damaged. And again, that's part of that natural immunity to other diseases, but it damages those cilia, so it takes weeks or months to recover until that's back to normal. Now, the causative agent is Bordetella pertussis. It kind of helps us there with the name. It is a gram-negative bacillus. It does have to have oxygen, and it can survive on various forms of nutrients. As far as some of its virulence factors, it produces filamentous hemagglutinin. That's what allows it to attach to our cells. What causes the whooping and the coughing is the pertussis toxin, produces massive amounts of mucus, and then again our body reacts to the buildup of mucus, coughing to get rid of it as it accumulates. Also produces tracheal cytotoxin, as the name implies, direct destruction of those ciliated cells, and that's why even after the infection during the convalescence, it can take so long to truly recover. And then, of course, it's gram-negative, so endotoxin, that LPS that's in the outer membrane of gram-negatives, cause that release of cytokines and that immune response. Now, there is a vaccine to the whooping cough. It is led to high vaccination, has kept the incidence low. However, we're starting to see more and more cases of it because of decreased vaccination. So it does require a booster after about 11 years, and it's common for people to not receive that booster shot. So again, 11 years. And those current vaccines are an acellular form of the antigen. So again, this is not, you can't get whooping cough from the vaccine. It just has part of the antigen, so the body is trained to recognize them. It's not like a weakened form or anything. Again, it's just providing part of it so our immune system can recognize it. So our summary table here, again, Bordetella pertussis, most of these you'll see is by droplet contact. As far as virulence, again, that hemagglutinin that helps it attach, and then various toxins, the pertussis that increases mucus, cytotoxin that kills the ciliated cells, and then that LPS or endotoxin because it's gram-negative. So again, that DTaP vaccination includes the whooping cough. So this is one of the required vaccinations. So that does help. However, again, due to changes in people not getting vaccinated as they should, again, that is leading to some increased cases of whooping cough. Now, a little bit about RSV. We won't talk a lot about it. Again, it does infect the respiratory tract, and the name Syncytia, that just means that it creates giant multinucleated cells. So essentially it recruits our cells and makes them join together into this large conglomeration of cells. The reason for that is it allows the virus then to move from one cell to the next without having to exit, where the immune system could detect it and then come back in. So it just fuses all the cells together and turns them into virus-producing factories. Now, some outbreaks of droplets have spread across the world. We typically see peak in the winter and the early spring. This one is particularly important in younger children, especially babies. So children 6 months or younger, especially prematures, are very susceptible to the disease, and it can be very damaging to them. It can continue into the toddler stage as well, but especially whenever infants, because their immune system is still developing and hasn't reached that peak yet. Babies up to the age of 6 and even after are extremely susceptible to this. And just a little FYI here. So in 2020, whenever all the protocols were happening for COVID-19, where again, we were wearing masks and we were social distancing, RSV infections dropped really low. Now there was kind of an unusual kind of wave in the summer of 2021 as people stopped wearing their mask and stopped social distancing. So again, typically it's winter, spring, but essentially what happened is after the regulations started to decrease for COVID and people started getting out more, not wearing their mask as much, that RSV spiked again. Again, our summary table, so droplet and indirect contact, again, its virulence is forming those syncytia, which is in the name, where it just joins cells together to allow it to spread. Now, passive antibodies can be used. Again, just using that terminology. Again, this is passive in giving somebody the antibody. So this is where somebody who has had RSV and they've built up antibodies, their serum would be taken, and those antibodies to RSV would be removed and injected into somebody. So they're not actually giving them any part of the RSV virus or any protein or anything that it makes. It's just directly giving them antibodies against it. So it's a passive antibody vaccination that can be used. All right, now the flu, we'll spend a good bit of time here talking about it because this is so common. It is caused by the influenza virus. There are 3 types, A, B, or C. They're all part of the Orthomyxoviridae family. And with these, there are 2 kind of main glycoproteins. So there's hemagglutinin and there's neuraminidase. And again, glycoprotein means a protein with a sugar attached to it. And that's what these guys down here are. So these glycoproteins, first of all, the hemagglutinin, so its name, it's agglutinating or just joining together red blood cells. So it causes them to clump. And this is also allows it to bind to our mucosa. So the hemagglutinin does 2 jobs. It helps with attachment and it helps to clump those red blood cells. And then the neuraminidase, this breaks down the protective mucus coating. So again, that's one of the protective barriers. So the flu can get in by breaking down the mucus and then getting into the cells. The neuraminidase also helps with budding and the release of the viruses once they're made, and they help fuse host cells to form those syncytia as well. This is also where the names like H1N1 comes from, or H2, and then the numbers. So H is for that hemagglutinin and N is for the neuraminidase. So the strains of the flu are named for the mutation or the variant of neuraminidase and hemagglutinin that they contain. And those are all found, as we see here, out on the envelope. So this is an enveloped virus. It's a segmented RNA virus, meaning it has 8 separate RNA strands. They're all unique. It's not like copies of the same thing. But instead of having one long DNA or RNA molecule, it has 8 segments or pieces of RNA. And then again, also has matrix protein that helps kind of hide it. But again, that envelope helps it to attach as well. Now, what happens with these, and the reason we have so many strains, and we talk about H1N1 or H2N2 or whatever the combination may be, is because of 2 phenomena. One is antigenic drift. This is what we've talked about with other viruses. So this is due to random mutations. So it's just the kind of gradual change or random change to the genes that make the hemagglutinin and the neuraminidase. but it decreases ultimately the ability of memory cells to recognize them. So if we had an infection to one and we created antibodies and we have those memory B or T cells, and then if it undergoes a slight mutation, now those antibodies may not recognize, or those memory cells may not recognize it. And that's also one of the reasons we have to get the flu shot each year instead of having lifelong immunity. Now, what's unique about this one that we haven't talked about is antigenic shift, and we have a picture on the next slide. Again, as I mentioned, it has 8 pieces of RNA. Well, what happens here is if 2 influenza viruses, like 2 different subtypes or strains, are infecting the same cell, they essentially swap out one of those RNA strands with a different influenza virus. So now this only can occur though if the infected cell has both subtypes. Okay, so say we had H1N1 and H1N2, and they were both in the same cell. Whenever the viruses are being produced, they could accidentally switch up some of the segments. And then that would change. It would be a completely new strain with a completely new combination of RNA. And when that happens, now, again, this is completely new, so our host cell memory cells don't recognize it, and it's this antigenic shift that has led to various influenza pandemics because it's a completely new, it happens very quickly instead of gradually like antigenic drift, and that can lead to these pandemics. All right, so this is showing that antigenic shift that we were talking about. And essentially here what happens is inside of the same host, and it doesn't have to be a human, it can be inside of, in this case, a pig or a duck or something. But what has happened here is that 2 different flu viruses, in this case, duck influenza virus and human influenza virus, have both infected this pig down here at the same exact time. And just to indicate the different types, one is blue and one is orange. So again, they both produce slightly different hemagglutinin and neuraminidase proteins due to their different genes. Okay, so again, each one of them have the 8 RNA molecules on them. And what happens is whenever both of these infect the same cell at the same time, and these viruses go to produce, to manufacture themselves, remember the RNA is made and then the capsid forms around it. Well, what happens with antigenic shift is in this case, this is the human influenza virus, and it wanted to put in 8 strands of that human influenza virus RNA. However, whenever it was putting its RNA in, it accidentally picked up one of the duck influenza virus RNAs. And in this case, now it's going to produce a completely new variation. So in the scenario that was made here, the hemagglutinin, that spike that was made that allows it to attach, it came from the duck. So it's going to have a similar host pattern, a similar binding, but the neuraminidase is still what was originally there from the human. But now we have a completely new strain or serotype of this influenza virus. And if we were immune to either the human influenza virus or the duck influenza virus, now we're not going to be immune to this one because we haven't seen it before. So now, again, in large enough quantities, it could lead to a pandemic. I mentioned before about the influenza vaccine. So there are 3 major types that are made in the US. There's an intramuscular that's an inactivated vaccine that has 3 strains of the flu in it. And so what the CDC does is they try to predict which strains we are most likely to encounter during kind of the flu season, the winter and the early spring months. This is based on data, it's not random, but again, it's only 3 strains. So whenever you are immunized, you are only immunized to those 3 strains of the flu. So people may say, oh, I had the flu shot, but I still got the flu. Well, that means they, unfortunately, were exposed to a strain they weren't immunized against. So it wasn't that the vaccine didn't work, it just only immunizes us to those strains. There is also another one that's intramuscular, again, inactivated, but provides immunization to 4 strains of the influenza. Again, inactivated means that it cannot reproduce. So the virus is there, but it has no way of replicating. So again, you can't get the flu from taking the flu shot. The fever and kind of an immune, sickness symptoms that you may feel after getting it is because you activated your immune system. That's the point of the vaccination, is to activate the immune system so we get immunity. It's not actually the flu. Again, the fever may spike because we just injected something foreign, but it can't lead to an actual flu infection. So again, scientists are continually researching these emerging strains, but because of especially antigenic shift, it's impossible to have this, completely, kind of universal flu. They are working on that. They will continue to work on it. There are some in clinical trials, but again, because of the mutations, it's really hard to target all influenza strains. All right, so our summary table, so again, A, B, or C viruses, droplet or indirect contact here. Again, the virulence are those glycoproteins, so the hemagglutinin and the neuraminidase, but also virulence is the ability to change rapidly, making vaccination and immunity really hard because of that antigenic shift and drift. So again, a few different vaccines available. There are some medications like Tamiflu. There's also Xofluza. Tamiflu is most commonly used. Again, it kind of needs to be used right away, and it just kind of helps decrease the replication. So it makes the infection a little less symptomatic than normal.